Have you ever been, really deep into studying, like for a big exam maybe? You're surrounded by notes, the textbook, and something just isn't clicking.
Oh, definitely. That feeling of just staring at the words.
Exactly. And rereading doesn't always help. But then maybe you try something active. You rephrase it in your own words, or sketch out a little diagram, or turn a paragraph into
Nice.
Q&A.
You transform it somehow.
And suddenly there it is, that aha moment. It sinks in. That whole active process, reinterpreting, restructuring, rewriting it. That's what makes it stick, isn't it?
It really is. Moving from just seeing it to actually, internalizing it.
So let's take that idea and pivot to large language models. LLMs, these incredible AI systems, right? They write essays, translate, code, amazing stuff.
Truly impressive capabilities.
But here's a thought, maybe something we don't consider enough. What if these brilliant digital minds actually struggle to learn and adapt on their own, in that same active, evolving way humans do?
That's a fascinating point.
Okay, so let's unpack that. It's a bit of a paradox. LLMs are powerful, trained on just unbelievable amounts of internet data.
Yeah, vast data sets.
But once that huge initial training is done, their knowledge is, well, it's mostly fixed, right? They don't naturally learn from new experiences or new info like we do. They're kind of brilliant, but static.
Mm-hmm. Locked in time almost.
And that brings us right to today's deep dive. We're looking at a really groundbreaking paper called Self-Adapting Language Models. They call it SEAL by Adam Swiger and colleagues over at MIT.
A very exciting piece of work.
So our mission today is to guide you, our listener, through this paper. We're going to dive deep, pull out the key ideas, and make it accessible, even if this is all new territory for you. We want you to be able to follow along, imagine the implications, as we explore how LLMs might move beyond just knowing to actually learning and evolving their own understanding.
And what's so fascinating here, building on what you said, is exactly that sixth nature. That's the fundamental problem SEAL tackles. Most LLMs, once deployed, they're trained, and that's it. Their knowledge is a snapshot.
Right.
So adapting them to a new task, maybe something super specific like a niche medical diagnosis or a unique legal question, or just feeding them new facts that came out after they were trained, it's usually a whole separate manual process.
Like fine-tuning or prompt engineering.
Exactly. External interventions. It's not the model learning on its own initiative.
Gotcha.
Now, think back to that student analogy you started with. A good student doesn't just passively absorb a lecture, right? They actively rework the notes, diagrams, summaries, self-quizzes. They're transforming the input.
Making it their own.
Precisely. And this paper asks, well, can an LLM do something similar? Can it go beyond just processing info and actually rewrite its own learning material, or even tweak its own learning process to get better?
So it's about the LLM taking control of its own learning.
That's the core hypothesis. SEAL basically says, yes, an LLM can self-adapt. It can do this by generating its own training data, transforming existing data, maybe even adjusting its own learning procedure.
Wow.
And this isn't just a minor tweak, it's a fundamental shift. It's moving AI from being a passive recipient of data, just taking what we give it, to being an active self-directed learner. That's potentially a game changer.
It really is an intriguing paradox. These pre-trained models, the ones behind the chatbots we use, they can do incredible things. Language understanding, generation. It feels like they've read everything.
Their foundational knowledge is huge.
Huge. Yet, despite all that power, getting them to adapt to specific new tasks or integrate fresh facts that weren't in that initial data dump or master some new kind of reasoning, it's surprisingly tough.
Yeah, it's a real bottleneck.
It's like they know everything they were fed, but they don't inherently know how to learn new things efficiently from, say, just a little bit of specific data, or how to process that new stuff in the best way for their own internal structure.
Right. They lack that meta skill of learning effectively.
And the why behind it is important too. Often it's because getting enough high-quality, task-specific data for fine-tuning is hard. You can't just whip up millions of perfect examples for every possible niche.
Data scarcity is a real issue for specialized tasks.
So traditional fine-tuning just takes the data as is, right? You feed it what you've got, and the model does its best.
Yep, that's the standard approach.
But here's where SEAL gets really interesting and potentially transformative. That as-is consumption means the data might not be in the best format for the LLM to learn from efficiently. And crucially, current LLMs can't really strategize. They can't decide, okay, this raw data needs to be transformed this way, or I should focus on learning these bits first.
They don't have that self-awareness about their own learning process.
Exactly. They're passive recipients. They rely on us humans to perfectly format and curate their learning materials.
That's absolutely right. And if we connect this back to human learning, the contrast is stark. Think about tackling a really dense textbook or a complex new subject. You don't just reread it endlessly hoping it sinks in.
No, that usually doesn't work very well.
Right. An effective student engages, they highlight, summarize in their own words, make flashcards, draw diagrams, connecting concepts, maybe formulate questions to test themselves.
It's all that active stuff.
It's that active assimilation, that restructuring, that rewriting that's absolutely crucial for deep understanding and long-term recall. It's how we make knowledge truly ours.
Okay.
Now, compare that to standard LLM training. Usually you give it a data set, and it learns directly from it. There's no built-in internal rewriting or assimilation step like humans do.
It just processes what it's given.
Pretty much. Either through fine-tuning, where it adjusts its weights based on the examples, or through in-context learning, where the info is just in the prompt, not changing the model's core memory.
Right, the weights stay the same in that case.
Exactly. And this paper's key insight is that this lack of self-directed data transformation, this inability to kind of process and reorganize its own learning material, that's a major hurdle for making LLMs truly adaptable and efficient learners. Without it, they're powerful, yes, but also kind of rigid, still dependent on us for optimal learning.
So if they're currently so static, what does this SEAL framework actually do? How does it give them this ability?
Okay, so SEAL basically equips LLMs with this new capability, generating their own training data and, maybe even more surprisingly, their own fine-tuning instructions.
Like the LLM becomes its own teacher and curriculum designer.
Sort of. Think of it like the LLM writing its own personalized study guide and learning plan. The paper calls these self-generated instructions self-edits, or SE for short.
Self-edits. Okay. What does a self-edit look like?
It's essentially a natural language instruction that the LLM generates itself. It specifies what data to generate, maybe reformatting info, distilling it, creating new examples, and sometimes even how to learn from it, like suggesting optimization settings, the hyperparameters.
How does it know what instructions to generate?
Well, the mechanism involves giving the LLM new information within its context window. Based on that new info, it then generates the self-edit and the resulting synthetic data. So it's reacting intelligently to new input by immediately thinking, how should I best learn this, instead of just passively receiving it.
That really does sound like taking agency over its learning.
It is, and the architecture SEAL uses is quite clever. It's structured as a two-loop system. Think of it as meta-learning. The system is learning how to learn more effectively.
Two loops. Okay, break that down for us.
Sure. First, there's the inner loop. They call it the update loop. This is where the action happens, so to speak. The model takes the self-edit, it just created that study guide, and uses it to actually update its own internal parameters.
Through standard training, like supervised fine-tuning.
Exactly, through SFT, supervised fine-tuning. The self-edit tells the inner loop what specific, hopefully high-utility data to train on, and potentially how to train on it. It's the engine applying the learning strategy.
Okay, that's the inner loop. What about the outer loop?
The outer loop is the overarching reinforcement learning loop, or RL loop. This is really the brains of the operation. Its job is to train the LLM to produce effective self-edits.
Ah, so it's learning how to make good self-edits. How does that work?
Right. So the model generates a self-edit. That edit gets applied via the inner loop, updating the model's weights. Then, crucially, the updated model's performance is tested on a specific task.
You measure if it got better.
Precisely. That performance difference acts as a reward signal. It's actually a simple binary reward, 1 if the model improved, 0 if it didn't. This reward then guides the model through reinforcement learning to generate better, more impactful self-edits next time.
It's a feedback cycle. Learn how to generate edits that actually help.
Exactly, a continuous feedback mechanism, nudging it towards becoming a more strategic learner.
Now, how does this differ from other RL uses in LLMs? We hear about RLHF, for instance.
That's a great question. RLHF, reinforcement learning from human feedback, is mostly about aligning model outputs with human preferences, making responses safer, more helpful. Other RL methods might optimize for better final answers or more logical reasoning steps, like in chain of thought.
Okay.
What makes SEAL unique is that it applies RL to optimize the generation of the self-edit data itself and the learning procedure that leads to the weight updates. It's not just about the final output, it's learning how to learn better by creating its own optimized training material.
It's optimizing the learning process, not just the result.
Precisely. The paper mentions using a specific RL algorithm called RESTEM. It's based on filtered behavior cloning or rejection sampling, chosen because it's stable for this tricky task of teaching a model how to create effective training processes that involve actual weight updates. It helps a model reliably figure out which kinds of self-generated data and instructions actually lead to performance gains.
That is a profound shift. Moving from just processing or answering to actually figuring out how to reshape its own knowledge. Let's see how this plays out.
Okay.
The paper looks at two key areas, right? First is knowledge incorporation. So
Yeah.
the goal here is what? To get new facts into the model's weights, its memory, so it knows them without needing the source text again.
Exactly. Efficiently integrate new factual knowledge so it can be recalled accurately, just from memory, without needing the original context again in the prompt, like asking it about a passage it read earlier, but not showing the passage again. It needs to have truly learned it.
Okay. And how does SEAL do that differently? You mentioned it doesn't just train on the raw text.
Right. Instead of fine-tuning directly on the raw passage, which, as we said, isn't always great for internalizing SEAL fine-tunes on synthetic data generated by the SEAL model itself.
Ah, the self-edits in action.
Correct. So the model reads a new passage,
Hmm.
then it gets a prompt to generate a self-edit, maybe something like list several key implications derived from this content or summarize the core facts. These generated implications or facts, this synthetic data, that's what the LLM uses to update its own weights. It's like our student reading an article and then writing down the key takeaways or consequences in their own words. Those become the optimized notes for future recall.
Internalized and ready to go. And they use LoRa for this. Low-rank adaptation.
Yes, exactly. Lurai allows for these lightweight, efficient updates. They're not retraining the whole massive model. They're adding and training small, specialized adapter modules. This allows for rapid, targeted knowledge updates without messing up the model's existing knowledge too much.
Smart. Okay, so what about the results? How well does this work for knowledge incorporation? They use the squad dataset, right? Testing recall without the context.
They did. And the baseline, just fine-tuning the Quen 2.57b model on the raw passage text, it barely helped. Accuracy went from about 32.7% to 33.5%, a tiny bump.
Which confirms that just reading isn't enough for deep learning.
Precisely.
Yeah.
But when they used synthetic data generated by that same base Quen model without SEAL's RL optimization, yet accuracy jumped to 39.7%.
Okay, that's a decent improvement already. Just generating some kind of summary helps.
It does. Then they tried using synthetic data generated by a much bigger, more powerful model, GPT 4.1. That pushed accuracy up to 46.3%. Pretty good. Shows that better synthetic data from a stronger model helps even more.
Right, makes sense. But here's the kicker, right?
This is the kicker.
Yeah.
Get this. SEAL, using the smaller Quen model, but with its RL-optimized self-edits, achieved 47.0% accuracy.
Wow. So the smaller model, using SEAL strategy, outperformed the raw synthetic data from the much bigger GPT-4.
Exactly. It's not just about the generator's power. It's about the intelligence of the self-adaptation process. The RL loop taught the smaller model to generate better data for itself than the larger model could provide off the shelf.
That's incredible. Does the paper show how it improves?
Yeah, if you're looking at the paper, Figure 4 really drives this home. It shows SEAL's accuracy climbing over the RL iterations, quickly surpassing the GPT-4 synthetic data performance after just 2 rounds of training. It visibly learns to make better study guides for itself.
And it generalizes. They tested it on more passages.
They did. In a continued pre-training, CPT setting, with 200 passages, SEAL still came out on top, hitting 43.8% accuracy, beating all the baselines. It shows the learned strategy isn't just a one-off trick. It generalizes.
And qualitatively, what do the self-edits look like as it learns?
Figure 5 gives a sense of this. Over the RL iterations, SEAL learns to generate more detailed, effective self-edits. It starts breaking down dense passages into what the authors call easily learnable atomic facts. It's essentially refining complex input into digestible knowledge chunks, perfectly tailored for its own learning.
Fascinating. Okay, that's knowledge incorporation. What was the second domain?
The second domain was few-shot learning. This is a really tough nut to crack in AI.
Right, learning a new task from just a handful of examples.
Exactly. Like seeing 1 or 2 solved puzzles of a type you've never seen before and then having to solve a new one. It requires abstract reasoning, inferring general rules from minimal data.
And they used the ARC-AGI benchmark for this.
Yes, the abstract reasoning challenge. It's designed specifically for this kind of abstract generalization test, often using grid-based visual puzzles.
So how does SEAL tackle this? It can't just generate factual summaries here.
No, here it learns to autonomously configure its own adaptation pipeline. Instead of a human figuring out the best data augmentations or training settings for a new, unseen orders task, SEAL generates these choices itself. It makes those strategic decisions on the fly.
What kind of choices?
It selects from a set of tools, things like data augmentations, rotating the grids, flipping them, resizing, maybe even chaining transformations together, but also optimization parameters, the learning rate, the number of training epochs, even deciding how to compute the loss function.
Wow, so it's like instead of me telling an AI how to practice rotations, then flips, the AI decides for itself, okay, for this game, I think practicing flips first, then rotations with a high learning rate for 3 epochs is the best strategy.
Exactly. It becomes its own intelligent coach and curriculum designer for adapting to novel problems.
Okay, and the results. They used a llama model for this?
Yes, Llama 3.21b instruct on a curated ARC subset. The baselines really show how hard this is. In context learning, ICL, just showing examples in the prompt, 0% success.
Ouch, just seeing examples wasn't enough.
Not at all. Then a method called test time training, TTT, using self-edits, but without SEAL's RL optimization loop, that got 20% success. Better, but still limited.
And the best possible case, the oracle.
Right, the Oracle TTT, where a human expert crafts the perfect settings for each task, that gets 100%. That's the theoretical ceiling.
So where did SEAL land?
SEAL achieved a 72.5% success rate.
72.5, that's a huge leap from the baseline.
A massive improvement. It clearly shows SEAL learned how to effectively adapt itself to these novel, few-shot reasoning tasks. Now, obviously, there's still a gap to that 100% Oracle score, so there's room for improvement. But the jump from 0% or 20% to over 70% is really significant. It highlights SEAL's potential for enabling LLMs to tackle genuinely new problems with much less human handholding.
It really seems to be learning how to learn in different contexts. So stepping back, why does this work so well? What's the core mechanism driving this success?
Fundamentally, it's the power of optimized self-editing. It's not just generating any synthetic data or picking any training parameters. Through that outer RL loop, it learns to generate the specific data and choose the specific settings that are most effective for improving performance on the target task.
It's tailoring the learning material and process perfectly for itself.
Exactly. That learning how to learn aspect, the meta-learning, is key. It's developing an efficient adaptation strategy, not just memorizing facts or rules.
And you mentioned the paper looked at how different starting prompts affected things, like asking it to generate implications versus rewrites.
Yes, Section C delves into that. They found that different initial prompts, implications long, rewrite, self-quy, could indeed set a decent baseline. Some prompts naturally led to better synthetic data than others, even before the RL training.
Okay, so good prompting still helps.
It does. But here's the important part. SEAL's reinforcement learning still significantly boosted performance on top of those strong initial prompts, gains of like 6 to 11 percentage points.
Ah, so the RL optimization adds real value regardless of the starting point.
Precisely. It shows the learning mechanism is robust. It's truly optimizing the utility of the self-edits, refining them beyond what even a well-chosen initial prompt can achieve. It's like a smart student figuring out the absolute best way to study, even if they start with a decent textbook. It finds what truly makes a difference for its internal understanding.
That makes sense. But like any new approach, it can't be perfect yet. This raises an important question. What are the limitations? Where does SEAL face challenges?
Absolutely. It's crucial to understand the current boundaries. The paper is quite transparent about this. One major challenge is catastrophic forgetting.
Ah, yes, the classic problem. Learning new things makes you forget old things.
Exactly. When a model keeps learning new information, especially by updating its weights, it can inadvertently overwrite or degrade previously learned knowledge or skills. It's like trying to learn Spanish and suddenly finding your French is getting rusty.
How does that show up in SEAL?
As the model applies more sequential self-edits, updating itself with new knowledge, its performance on the earlier tasks it learned starts to gradually decline. Figure 6 in the paper illustrates this performance doesn't totally collapse, but there's a noticeable downward trend on older tasks as new ones are learned.
So it's not a complete wipeout, but it's an issue.
It's definitely an area for future work. They suggest things like reward shaping, designing the reward to penalize forgetting, or integrating known continual learning techniques to help models better retain old knowledge while acquiring new stuff. Managing this trade-off is critical for any truly adaptive lifelong learning system.
Okay, forgetting is one thing. What else?
Another significant factor is computational overhead.
Ah, the cost. How intensive is this process?
Well, remember that inner loop. It involves fine-tuning and then evaluating the entire model for each self-edit to get the reward signal for the outer loop. That's much heavier than, say, RLHF, which might just need a quick forward pass.
So fine-tuning and evaluating every time, that sounds slow.
It is. The paper mentions it takes about 30 to 45 seconds per evaluation. So running a single round of RL training for the knowledge incorporation task took them around 6 hours on pretty powerful GPUs.
6 hours for one round, that's substantial.
It's significant overhead. This cost makes it challenging to scale SEAL to massive data sets or use it for rapid real-time adaptation in a live system. Finding ways to make that inner loop update and evaluation process more efficient is a key research direction. Maybe better parameter-efficient tuning methods or different architectural approaches.
Makes sense. Cost is always a factor. Any other major limitations?
One more, which is quite interesting conceptually, context-dependent evaluation.
What does that mean?
Currently, the way SEAL is set up in the paper, it assumes that every piece of new information, the context, comes paired with some kind of explicit, predefined downstream task for evaluation. For the few-shot learning, you had those ARC query-answer pairs. For knowledge incorporation, you had passages bundled with specific Q&A sets.
Right, you need a way to measure if the self-edit actually helped.
Exactly. That makes calculating the reward straightforward, but it also limits the applicability. You can't easily train SEAL on just a massive pile of raw, unlabeled text like the entire web, because you don't have those pre-made evaluation sets readily available for every single piece of text to provide the reward signal.
So it needs structured tasks right now.
As implemented in the paper, yes. But what's fascinating here is the potential solution they propose for the future.
Oh, what's that?
The model could potentially learn to generate its own evaluation questions. Imagine the LM reads a passage, and then, while the passage is still in context, it drafts its own Q&A pairs relevant to that passage.
It generates its own test.
Exactly. This self-generated evaluation could provide the immediate reward signal needed for the RL loop, without relying on external predefined tasks. This would massively broaden SEAL's potential, allowing it to learn and adapt from vast, unstructured corpora, paving the way for truly autonomous, continuous self-improvement on almost any data.
That's a really cool idea. Self-supervision for the adaptation process itself. Okay, so bringing this all together, what does this mean for the bigger picture? Where is LLM development heading?
Well, this connects directly to a critical issue facing the field, the looming data wall.
The data wall, meaning we're running out of training data.
Essentially, yes. There's research, like from Villalobos and others, projecting that the most advanced LLMs, the frontier models, are on track to exhaust all the high-quality, publicly available, human-generated text, data books, articles, websites, transcripts, possibly by 2028.
2028, that's really soon.
It is. Think about it. Once we hit that wall, progress in LLM capabilities can't just come from feeding them more human data, because there won't be any significant new high-quality sources left to consume. We'll have used it all up, so to speak.
So how do models keep getting better then?
This is where the paper argues that synthetic data augmentation becomes absolutely necessary. If human data runs out, future AI progress will likely depend heavily on a model's ability to generate its own useful training signals.
And SEAL provides a way to do that intelligently.
Exactly. SEAL offers a concrete path forward. By enabling models to generate their own optimized high-utility training data, it's not just an interesting research idea. It could become an essential tool for continued progress beyond the limits of available human data. It's a potential solution to a very real scarcity problem looming over AI development.
Wow. Okay, so beyond just overcoming data limits, what kind of future does this enable? What's the vision here?
It paints a really compelling picture for self-learning and potentially truly agentic AI. Imagine an LLM reading a complex new scientific paper. Instead of just giving you a summary, it could then, using its existing knowledge combined with the new info, generate tons of its own material, detailed explanations, diverse summaries, challenging self-quiz questions, maybe even formulating new hypotheses or implications.
All generated by itself for itself.
Right, and then it could use that self-generated material to deeply refine its understanding, internalize the concepts, improve its skills, all without needing more direct human input for that specific topic.
That sounds like a continuous growth loop.
Exactly. An iterative loop of self-expression and self-refinement. This could allow models to get much better, especially on niche or complex topics where human data is scarce, just by thinking and generating for themselves.
How does this connect to things like chain of thought?
That's a great connection. Current models use RL to produce better reasoning traces, better chains of thought. SEAL could be a powerful complementary mechanism. Imagine a model learning when and how to trigger a weight update mid-reasoning to maybe correct a misunderstanding or strengthen its grasp of the problem space.
So it could learn during the thought process.
Potentially. Or maybe after completing a complex reasoning task, you could use a self-edit to distill the key insights or the successful strategy directly into its parameters, making it better prepared for similar problems in the future. It's about internalizing the learning from reasoning, not just producing a better output once.
Making future inference better through internalized experience.
Exactly. And this naturally leads to the idea of agentic systems.
AI agents that act and learn over time.
Right. Models that operate over extended interactions, needing to adapt dynamically to new information, changing goals, evolving environments. Think of a sophisticated personal assistant or a robot interacting with the world.
They need to learn continuously.
They do. And SEAL enables what the paper calls structured self-modification. After an interaction or maybe a series of experiences, the agent could synthesize a self-edit summarizing the key learnings. That triggers a lightweight weight update. This allows the agent to actually develop over time, align its behavior with its experiences, and become less reliant on constant external supervision or reprogramming. It's a crucial step towards building genuinely autonomous, evolving AI agents that learn from experience, much like living organisms do.
This has really been a fascinating deep dive. We've gone from how we learn by rewriting notes to how LLMs might start doing something similar. SEAL really shows these models don't have to be static.
No, they can potentially learn to generate their own best learning material and apply it through these lightweight updates.
It's a pretty profound shift, moving from just passively consuming data to maybe actively shaping their own learning process.
It really reframes how we think about AI learning.
So for you, our listener, as we wrap up, here's something to chew on, a provocative thought. Imagine a future where your digital tools, your assistant, the AI in your car, maybe systems helping scientists aren't just reciting facts or following rules. Imagine they are subtly, constantly, autonomously getting smarter, learning from every interaction, every new piece of data, almost like how we reflect and learn from our own experiences. What completely new possibilities might open up when AI can genuinely reflect, adapt, and refine its own understanding moment by moment continuously.
It's a future with potentially very different kinds of AI.
Indeed. Thank you so much for joining us on this deep dive into self-adapting language models.
Always a pleasure to explore these cutting-edge ideas. Really pushes the boundaries.
Until next time, keep digging deeper.